the previous video, we have looked at how is it possible to reconstruct a time domain signal from the samples of the frequency domain signal. The time domain signal, usually given as x of n, has been transformed into the x of omega using the Fourier transform, and the samples of this Fourier transform, because the Fourier transform over here is a continuous function of the frequency, and therefore it is not possible to be stored or processed by real time systems. So, we need only the samples of these. We have taken equally spaced samples of x of omega and hence obtained x of 2 pi by n k. So, this can be, even in simpler way, can be written as x of k also, because you can observe that 2 pi as well as the capital N, they are all constant, and only this k is a variable. So, I can represent a function as a x as a function of variable k. So, this way we can represent x of omega. We have shown that the signal can be exactly recovered from the samples and reconstructed from the frequency domain samples. Now, question is, what should be the length of the n? So, as seen in the previous section, the number of samples taken from x of omega, be it capital N, it should be ensured that this n is greater than or equal to the capital L. The capital L over here is nothing but the length of the signal. For example, if x of n is this signal, assume x of n is a 2, 3, 1 and minus 5. If this is a signal, then length of the signal is 4. Therefore, the frequency domain representation of this, that is x of k, should be having at least a length of n is equal to 4. If the length is at least 4, then we will be able to exactly recover the time domain signal. This is the interpretation of the representation. Now, the discrete Fourier transform. Let us look at how we can obtain the discrete Fourier transform of a time domain signal x of n. So, this is the representation, or this is the formula for transforming an x of n, that is time domain signal, into frequency domain signal. As already mentioned previously, the length of the signal L and capital N are to be judiciously chosen. As far as n is concerned, it should be any number greater than or equal to the length of the signal. Using this representation, we can transform a given signal x of n into frequency domain representation. Since we have obtained samples of the frequency, this particular representation is called as discrete Fourier transform. So, if you can recall from the previous discussion, the x of omega is this way, and it could be periodic like this, right? And we would have taken the samples, discrete samples at various frequencies, and each of these frequencies are equidistant samples over a period of 2 pi. So, 2 pi, and these equidistant, since you are taking the samples of the frequency, this particular representation of signal is called as discrete Fourier transform, since the samples are from the frequency. When you take the inverse of this representation, let us look at the previous graph here. So, x of n to x of k is understood. From x of k, when you take the inverse Fourier transform, so I can write it as the inverse Fourier transform. So, if I take the inverse of this particular representation, do I get back the x of n? No, we will be getting back the xp of n. So, xp of n has been nothing but the periodic representation, periodic repetition of x of n. So, there must be some relation between the xp of n and x of n, and how we recover x of n from xp of n. So, the relation is already known to us. So, x of n is equal to xp of n itself over n greater than or equal to 0 and less than or equal to n minus 1, and rest all places it is 0. So, this is the way in which we can recover x of n from xp of n. There is a more elegant way of obtaining the x of n. This representation shown on the screen is called the IDFT, that is inverse discrete Fourier transform. So, you can observe that summation, in the summation you have the x of k, that means the frequency domain representation, and then multiplied by e raised to j 2 pi by n kn, and the students are to not miss this n over there. So, dividing by n. So, this is our analysis as well as synthesis equation. So, the screen the equation now shown on your screen is the synthesis equation. The analysis equation is giving you the information of what all frequency contents that are present in the discrete in the given time domain signal. Now, let us also look at some of the properties which make the DFT a special type of representation. First one is the periodicity. Both the DFT as well as IDFT are periodic with a period of n. So, capital N is the period of the Fourier transform or discrete Fourier transform. So, it means that if x of k plus n is there, it is nothing but x of k itself. That means this x of k repeats periodically with the period of n. It can be proven very easily. So, we know that x of k is summation x of n e raised to minus j 2 pi by n k n. N is equal to 0 to n minus 1. Now, this if I were to replace k by k plus n, then what would happen? So, this is summation x of n, there is no change in this, and the index of summation n is equal to 0 to n minus 1, this also does not change. Here it is e raised to minus j 2 pi by n, this also does not change, but only this change is here, that is k is now k plus n into n. So, if I were to expand this representation here, you will get x of n into e raised to the first term, that is e raised to minus j 2 pi by n k into n into e raised to minus j 2 pi by n into n. Now, pay attention to the second term over here. So, the second term which is highlighted over here, right, this term is the n get cancelled over here, and this whole thing is e raised to minus j 2 pi into n. So, you can observe it is nothing but cos of 2 pi n minus j sine of 2 pi n. So, n, what is the range or what is the value of n? N always takes integer values. Integer multiple of 2 pi is again 2 pi. So, cosine of 2 pi n will always be 1. So, this value is going to be 1 and this value is sine of 2 pi n, this is going to be 0. So, we can represent this as 1 minus j 0 or in simpler terms just as 1. That means this whole term over here, this term is equal to 1. And look at the remaining term. So, this x of k plus n, and this range is not changing, this is 0 to n minus 1, the n minus 1. So, this remaining term shown underlined here, that is summation x of n e raised to minus j 2 pi by n k n, n is equal to 0 to n minus 1, resembles the first equation. Suppose if I call this as equation 1, it resembles equation 1, that is this whole thing is nothing but x of k. So, we started from x of k plus n and it is equal to x of k. So, what does it mean? It means that the DFT is periodic. We have seen that the DFT is periodic. On the same lines, it can be shown that the IDFT is also periodic. We can use the same expression as the previous one, that is x of k plus n. So, now it is going to be smaller x of n. So, we remember that the x of n is used to represent the discrete time signal, that is time domain signal, and the x of k is used to represent the frequency domain signal. So, we can use the same principle and show that the DFT as well as IDFT, both of them are periodic. Now, while representing, you can observe in your textbooks that while representing the term e raised to minus j 2 pi by n k n, right. So, there are so many terms associated with this factor. There is exponential term, there is j operator, that too negative j operator, there is 2 pi, there is divided by pi, multiplied by kn. All this representation is simplified in this form. So, we use something called as W, and this n is shown here and raised to kn, that is e raised to minus j 2 pi by n kn is replaced by W n raised to kn. This is usually the method in which the textbooks represent the twiddle factor. So, this we will call it as twiddle factor. So, this is the twiddle factor. Now, this represents n point twiddle factor. So, there can be something like a W4 raised to 2. So, what is W4 raised to 2? So, here as you can see the value of n is 4. That means it is a 4 point twiddle factor. So, let us explore these in detail by considering one numerical example. Let us consider the determination of discrete Fourier transform of a given signal. So, the given signal can be x of n equal to 1 minus 1 2 minus 2. Some basic observations about the signal before we apply the known formula. So, what is the length of the signal? Length of signal is 4. Therefore, what must be the n? What should be the capital N? So, from the previous discussion, we know that the n should be greater than or equal to L. So, in this case, therefore, n should be greater than or equal to 4. So, let us consider n is equal to 4. Therefore, what we are going to determine further is going to be called as 4 point DFT of x of n. Okay, what will that be? That will be the x of k. So we will be interested in determining the 4-point DFT of the given signal x of n. What is the formula? So we know that the 4-point DFT x of k is summation x of n e raised to minus j 2 pi by n kn. Okay, so you know this relation. So in place of n, I can write the value 4. So this is 4, and we also know that the range of a small case n is 0 to n minus 1, that is 4 minus 1, which will be 3. So this is the representation. This can also be represented as x of n equal to summation x of n w 4 raised to kn, n is equal to 0 to n minus 1. Since I have considered capital N is equal to 4, I can make out that it is n minus 1 is 3. Now, as per this relation, n should be greater than or equal to 4. You can have even 5-point DFT or 6-point DFT or 7-point DFT, 8, 9, 10, any such number of DFTs, all are valid DFTs, or all of them are going to give back x of n while reconstructing. If n is 3 or 2, that means you will not be able to get back the time domain representation. Now coming back to, there is this, this is not the representation, it is x of k. So this is x of k. This correction has to be done, x of k. X of k is summation x of n. Now if I were to expand this relation, this expression, what will it be? It will be for n is equal to 0, it will be x of 0 into w4 raised to k into 0, which is the variable k into n is 0. So it is x of 0 into w4 raised to k into 0, plus the next value is x of 1 into w4 raised to k into 1. So I shall write it as k only, plus x of 2 into w4 raised to k into 2. I can write it as 2k, plus x of 3 into w4 raised to 3k. Okay, so we can represent the whole x of k in this way. It is an expanded form. So let us substitute the values of x of 0. So what is the value of x of 0? X of 0 happens to be this signal, that is x of 0 is 1. So I can replace it as 1 into the signal. What is the twiddle factor? That is w4 raised to k into 0. It is k into 0 is 0, plus you can observe the next sample, that is x of n, x of 1 over here is minus 1. So let us write signal value as minus 1 into w4 raised to k. On the same line, what is x of 2? X of 2 is plus 2. So it is going to be 2 into w4 raised to 2k. And finally, it is x of 3. X of 3 value is, this value is minus 2. So let us incorporate that in the expression. So write it as minus 2 into w4 raised to 3k. Okay. So the whole expression is in terms of only the k value. So the very first term, if you observe, it is 1 into w4 raised to 0. You can even further simplify it as x of k equal to only w4 raised to 0 minus w4 raised to k plus 2 into w4 raised to 2k minus 2 into w4 raised to 3k. This can be called as equation A. Now, what is equation A? What is it telling? The equation A is telling that the x of k, that is the DFT, that means discrete Fourier transform of x of n, is written in terms of these twiddle factors, that is w4 raised to 0, w4 raised to k, w4 raised to 2k and w4 raised to 3k. What is the range of k, and accordingly the values will change. Previously, if you see, the range of k is also from 0 to n minus 1. Here I have considered n is equal to 4. Therefore, k will also be ranging from 0 to 3. So, if you substitute k is equal to 0 in equation A, you will get a different value. If you substitute k is equal to 1 in this expression, you will correspondingly get a different value. We will continue this solution to this particular example by studying the factors, that is twiddle factors, in a bit detail.